Yes, welcome back everyone. So last time we were looking at machine learning operations for our project, and we looked at how to deploy it and how to interact with it and predict points. So today we are going to look at something new, and that is explainable AI techniques. Explainable AI is just are just techniques that help us understand and interpret results of our models. So we are going to interpret, or we are going to use some of the XAI techniques on our best and worst performing models. So our best machine learning model was the XGBoost, or the extreme gradient boost model, and the worst performing was the quantum machine learning model. So to begin with, we applied future importance using random forests on the best performing model, which is the XGBoost, and and we saw that the most used feature in determining the points of FPL players was the BPS, and BPS is the bonus point system. So this feature most influenced the model's performance in predicting the points for each player, or classifying the player as a high performer or low performer. Then some of the high performing features were ICT index, which includes the influence, creativity, and threat. Then minutes played by a player, the influence, threat, goals considered, and so on. So, so this was the visualization of the feature importance as a result of the random forests we used on the XGBoost model. So to go further, we applied what they call the sharp technique, or the sharply additive explanation technique on our best performing model. And also, simply to explain what sharp technique is, this technique is just an explainable AI technique that uses some sort of game theory to explain the output of a machine learning model. So it does this by by simply calculating the contribution of each feature on the model's performance by assigning what we call Shapley values. And these values are the ones that are used to quantify how the feature influences the model's output, or the accuracy, the recall. Yeah. So we use this technique on the XGBoost model, and by quantifying the contribution of each feature, also as we saw in the feature importance visualization, here also the BPS emerged as the most influential feature in determining the output of the XGBoost model. But the only difference is that the top 5 features changed. As we can see that in the feature importance, we had the top features as the ICT index, minutes, and influence. And then in the sharp technique, we have ICT index coming before, influence coming before the goals considered. So here, the Shapley technique indicated that the BPS, ICT index, and minutes influence the output of the XGBoost model the most, and we further came up with a plot for the most influential feature, which is the BPS. So here, each point on the graph indicates the individual player. So, and these players are plotted using a scale of the selected by percentage or the popularity of the players. So this visualization simply shows how the model classifies whether a player is a high performer or a low performer based on the BPS. So as you can see here from below, as the BPS increases from -1 towards 5, but between -1 and 0, we see a steep increase in the sharp values, indicating that as the player's BPS increases, also shows that the BPS of the individual player has an influence on the points being predicted for a particular player. So indicating that BPS has a positive correlation with the prediction, the points of the player. So we can see also players with a high BPS have high Shapley values, indicating that there is a positive correlation. So as a player has more BPS, indicating that there's a high influence on the model's, on the prediction of his points. So for example, like players like Mo Salah or Haaland, of course they'll have bonus points according to their performance, and yeah, according to the visualization, they will have more Shapley values according to the visualization. So to go further, this is just an explanation for the BPS for the Shapley values. Then we also implemented the technique of PDP, or the partial dependence plot for for the quantum model. So the quantum model was the worst performing model, and it was supposed to be the main model for the project, but due to computing resources, maybe all the model requirements, it emerged as the least performing. So being the least performing, we wanted to apply an explainable technique on the model, and we used the PDP. So PDP is just a technique that visualizes the marginal effect of a feature on the predicted outcome. So marginal effect means as the model, as the values of the features change, how does the prediction change? So the top 3 features here were selected: the BPS, ICT index, and minutes. So we wanted to see as the BPS changes, what happens to the prediction, and also as ICT index changes, what happens to the prediction, and what happens when the minutes change. So according to the visualization for BPS, we can see that now on the x-axis is the actual BPS of the player, and the y-axis is the average prediction as that value changes. So you can see as BPS drops, also the prediction drops, indicating there is an influence on the performance of the model. So the average prediction of the BPS on the model was around 0.27 there. So it was the average prediction for the BPS. And the most performing feature for the quantum machine learning model was the ICT index, indicating that here in between 0 and 1, or 1 and 2, there was a high prediction of 0.7, but that changed for the minutes, which dropped to around 0.6, which was the average prediction. So this indicated that the relationship between the features was more complex, as the graphs were very much non-linear, and very few parts of the graphs were linear, so indicated confusion between features, and maybe that's why the quantum machine learning model emerged as the least performing. So this is just an explanation for graphs. So for the BPS, the X indicated the actual BPS for the feature values, and then the Y, the average prediction. So we saw that as the BPS increases, the prediction decreases and reaches a minimum point, as we saw in the graph, minimum point around between 1 and 2 from the actual BPS. So here, indicating that very low BPS, the very low BPS values tend to correlate with the high probability of a player being a high performer. So as the BPS decreases, so does the prediction, indicating that there's a positive correlation between a player having high BPS and being a high performer. And yeah, also the ICT index, we saw that the increase in the values of the ICT index increased up to a constant point or a plateau at around 0.7, also indicating that high ICT index values are strongly associated with the high predicted probability of a player being a high performer. So also as the ICT index values increase, so does the model prediction, indicating that the ICT index has high correlation with predicting whether a player is a high performer and therefore having more points on a game week. And finally, the minutes. So as the minutes increase, so obviously as a player plays more minutes in the game, there's a higher chance of them being high performers as they play 90 minutes. So meaning they are very crucial for their team, and therefore shows that more minutes a player plays, the more likely the player is to be a high performer. So that was the partial dependence plot, the quantum machine learning model. And in conclusion, we see that the sharp technique for the XAI or the XG boost, since we used feature importance, there was a less increase in the accuracy. I think it was from 0.903 to 0. Around it was a less than 1% improvement, so indicating that that technique didn't have much influence on the accuracy. And however, the plot indicated that the model relies more on BPS and ICT index to predict whether a player will have high points on a game week. And for PDP, the quantum model relied more on ICT index to predict whether a player will be a high performer or not. Yeah, and those were the XI techniques we used for the best performing model and the worst performing model. Yeah, thank you.